now we're going to move on to the hardware demo that we've been talking about all morning. So the demo will be presented by Rolf Hilgendorf, and Idan Shmuel will be assisting with the demo.
With the problem of sampling a wideband about 1 gigahertz with one number of band-limited signals. We want to sample this with Sub-Nyquist rate, and the solution we have heard about before was the modular wideband converter. This picture we have seen before, and what we really want to do here as a first step was to take the front end and make out of it some real hardware. First, we have to think about some design parameters if we're doing hardware. We need to know how many slices we are doing here, how many slices is our original signal. We decided on 120 slices, which is giving us a bandwidth of 60 megahertz for the RTF, and because we want to sample it, many of the commercial A2Ds are available with 4 channels, so we decided on 4 channels. This would limit us to a very small number of signals we can detect. So we, and Bora showed this, that we have the possibility to have a lot of information in one channel, or a lot of channels with one small information. We decided to have 3 slices combined into one each channel. This gives us 60 megahertz for our A2B converter. So the front end we split into 3 parts. The first part is the generation of the periodic waveform. The second part is then the modulation, and the third part, the A2B converter. The periodic waveform we see here, and Bora talked about it, is alternating between 1 and 0. The clock rate of this signal is 1.8 gigahertz, and we have 108 bits at this clock rate, which form our periodic signal, and from this we can calculate the 60.66 megahertz. We are very much interested in the spectrum, and you see here one more time the spectrum of the original signal, and you can see that the peaks are 16 megahertz apart. So the cone you see here, it's are Diracs at 16 megahertz apart, or 60.66 megahertz. And as I said before, we are not really interested in the signal, in the time domain. We are only interested in the spectral properties of the signal. The second, the modulation board. Here we are splitting our input signal into 4 signals. We have the set of our mixers, and here we have the set of filters to give us the filtered output of 25 megahertz. One more time here at the beginning, we have the input signal, which is between 0 and 1 gigahertz, and has, in our case here for this example, 2 signals, one PM signal and one FM signal. You can't really see this in this small picture, but down here, as you can see, is a blown up version. This is FM, and this is a PM, modulated signal. Over here on this side, you have now the Elias signal, the 3 slices. So we have 3 times the FM signal, and we have 3 times the PM signal folded together into the 3 slices. And you see, I would put here, from every output, you wouldn't see much difference in the spectrum, but you see the difference in the time domain. You really you can follow. These are the same input signal taken together, and you see because of different modulation with our function, we have different signals. On this differences helps us to reconstruct the signal in the later mathematical operations. So what we have here is the modulated Wideband converter front end, and this is then now going to be going to our demo system 1. The system was demonstrated at the ISCASP 2010 at Dallas, Texas, at the NI booth, and you can see here Jonina together with the CEO of NI and Professor Oppenheimer, and now we are going to do the first demo. And I'm switching over to the demo screens. So, I have to speak louder, but you see here the demo system, which consists of the RF area here, which is producing our signal, which is combined, the two signals which we have from the two generators, it's combined, and it's going from here into the modulator, the modulator card, which has 4 outputs. I'm currently feeding 2 of the outputs back to the digitizer and 2 outputs back to the real-time scope, which has 6 gigahertz bandwidth, and we are used to show you the real input. We have up here the live system. We can, at this area, select the frequencies, which are, as I said, inputs here, combined, going through the digitizer. That's a picture of them. And if you are changing now our frequencies, you can see them moving up here. You see this sinus signal move from this point to this point. This is an FF signal. If you're moving this one, so even you have a very small move here for the 200 megahertz signal, went here because this is a 30 megahertz alive signal, and if you change the modulation of this first signal to PM, you see that the modulation, it really doesn't matter to the converter. It gives the content of the signal through, and if you are going now to, I have here only 100 and 200 megahertz. If you go to some other very high difference, so that we choose the first one to be sinus at 200 megahertz and FM at 800 megahertz to make it really see. You can see here the 2 signals, and I think it's a little bit hard to see that there is a peak. They are even lies one on top of each other here. If you switch now to the oscilloscope, then it's easier to see. So we have here the 200, about 250 megahertz signal. We have here at the end is 800 megahertz signal. This is a scale from 0 to 1 gigahertz. We have here our frequency spectrum of the periodic waveform, and here we have from sample to the scope between 0 and 25 megahertz our 3 signals on top of each other, and it's too dark to see the sinus on top of here. Okay, I think that was the first part of the demonstration. So what we have, as we saw, was the demonstration, and we have here the recovery algorithm, where the recovery is done in MATLAB, and it consists of the CTF part and the real-time slice recovery. But what we want to do really, if you want a real system, we have to do the signal processing part also in hardware. So we started some projects, multiple student projects, to convert this reconstruction part into hardware. We have here, it's the first part, the expander, the CTF, the rest is in the DSP, and we also had to construct test environment. I'm going very briefly through each of those steps. So the expander, as I said, we had at the beginning 4 channels, and each channel contained 3 signal parts, and we were sampled at 60 megahertz. We are expanding this to now to 12 channels. Each of them is 20 megahertz wide, and those 12 channels are then fed to the CTF. You can see here the 3 filter banks, which allows us, here's a more detailed picture of each of one of such a channel, the modulation part and the polyphase filter in order to get the 60 megahertz input signal into 3 separate 20 megahertz output signals. The CTF, you have seen this equation at Bohr's talk, so I'm concentrating on the beginning here. We have constructing the energy matrix, and because we have want to have it continuously, we have made some trade-off between the number of frames at the beginning and the signal-to-noise ratio, and we found that we have about 97% recovery rate at 70 input frames. There's no much difference between the Q frame and the V frame, so we are not doing these separation between from Q to V. We are actually working here with Q and finding our support on the Q matrix, and this is the OMP algorithm where if we are using for the detection of the support, and it has been also adapted to be working in hardware. This is really the block diagram and the VHDL for the different parts of the CTF. Finally, we have here the DSP, which is performing the rest of the task. So we get from the expander the samples, and it gets from the CTF the supports. We first have to do the inversion of our matrix. This is try to invert, and if it is one line in MATLAB, it occupies some portion of the FPGA, and we have adapted this one also to hardware by using house order reflection in the QR decomposition. Here is the reconstruction of the slices. Some people have asked before, what is with the time we need for the CTF to detect the support and so on. So we have here some delay memory, which is counting for the time we need for detection of the support and which we need for the inversion of the matrix. It is not a very big memory. It has about 250 samples, so that is the total latency we need from the beginning. We said we need 70 pulses, and then the calculation, it's about around about 250 samples which we store in the memory. So we have a delay between the beginning and the output of this 200 samples at 20 megahertz. One important thing here is the detector, which is working on the on the samples which are directly coming from the expander in order to find out if there was a change in the support, and then it's triggering the CTF again. Here is an example. For all of this parts, we developed a GUI. So in this case, it's a GUI for the CTF. In order to do the test, we can input some files. As input files, you can tell where you want the outputs to go, or you can select here parameters. Like here, you see the 70, the number of frames you can select here to perform our test on real hardware. What we have here is the environment. We have done our development on the detailed Rockstar board, so every of the FPGAs is a separate FPGA here. On the FPGA, we have input memory and an output memory as a FIFO, which was easy to access through the compute, through the GDL, from the computer through the GDL. We have the normal development real-time logic analyzer. And what we did is we had an input stream, we had a MATLAB version of the CTF, we had the CTF in hardware, and then at the end we compared both of them and did it on a lot of samples, so to make sure that we always did the recovery of this. So what did we have now was 3 FPGAs which contain tested parts of the reconstruction algorithm, and we had the signal generation and the front end, analog front end, and we need to do some system out of it. So as the next step, we have to integrate the A to D converter, and we have to do some control to get our system. But such a system, as you see here, is a heterogeneous system, and it's not very easy to go to a demonstration with such a heterogeneous system of 5, 6 parts. So what we really wanted to do is to integrate everything into one system. Only the NWC at the front end, we want the integrated system, and here I came in with the FlexRio FPGAs, Silence FPGAs and FlexRio, which are a part of the system, which has communication between each of them and easy access to all parts. We can go there. And so what we really had is a demo system 2, which you see on this side here. Behind this bar here are the FPGAs sitting, and so on. And I'm going to, this has been then demonstrated at the ISCAS conference in Rio de Janeiro this year. And the demonstrator is here too. Okay, on this screen you are now seeing here some input and here the reconstructed output. If we load our input, this is the next one. Now we have the demo effect. Okay, so again, here are our 3 slices from one of the inputs, or one of the outputs of the MWC coming as an input to the expander. The CTF is calculating our support and tells us which frequency this input came from. Here we saw in the last time we chose around 250 megahertz, and the second one, the sinus, from about 800 megahertz. And this is the contents of the slice, the FM signal, and here is the signal, the sinus signal, and as you see, this is about 40 dB above the noise floor here, and here is nothing to be seen from the sinus signal, even they have been here always in the input signals. Yes, I'm going back to the so where to go from here, our roadmap. We have shown that we have covered the medical imaging with Noam's talk, that we have covered now the cognitive radio part with Deborah's talk and my talk, and we hear a little bit more about the radar part in this afternoon session, and we have seen in one talk also the optic part, and we would like to develop for all of those parts ASICs to be employed in this one, and this is recovered the entire spectrum with our Sub-Nyquist sensing. In conclusion, we presented here the first Sub-Nyquist wideband receiver. We showed that the theory behind these receivers can be extended to a lot of areas. Our approach paves the way for high benefits application ranging from medical to optics, and it allows breaks in the current technology limits.
Okay, thank you very much. In the interest of time and in the interest of probably people starving in the audience, I think it's a good time to break for lunch, and any questions that you might have on the demo, you could just catch Rolf or Dan or me or anyone else from the lab, and we could chat over lunch.